It's pretty tricky to change or manage a switch policy if we don't know what it is or how to do it. In this nugget, we're going to solve both those problems in the hands-on lab. I'd like you to take a moment and look at this representation of a virtual switch that's in our vSphere environment. There's a lot that we can learn just by looking at the graphic. Starting on the left, we have a VM kernel port. The label for that VM kernel port is management network, and the VM kernel adapter is VMK0 with the IP address of 192.168.1.102. Based on that IP address and our topology, we know that this is a virtual switch on ESXi2 because that IP address belongs to ESXi2. Also looking at this graphic, we have a VM port group called VM space network. This is the default VM port group that was created when we deployed the ESXi host. And currently we only have one virtual machine that's still connected to that original VM port group. And that happens to be our vCenter server appliance. And when we deployed the vCenter server appliance, that was the only VM port group that existed on any switches. And so the VM port group named VM space network is the one that it uses. And if we use the arrow here to expand the virtual machines, it would show us explicitly that it's the vCenter server appliance that's the VM that's associated with this VM port group called VM space network. We also have the uplink, which is the uplink between the ESXi host and its virtual switch out to the external network. And in this example, we're using vmnic 0, which is our first vmnic. And vmnic 0 is what we used when we deployed originally our ESXi host for connectivity to that external network. And that means that by default, this is also vSwitch 0, which is our first standard vSwitch that's created for us automatically when we deployed the ESXi host. Now, regarding this switch and the actual port groups, there are vSwitch policies that are currently in place. We should be aware of what they are. And secondly, we also should be aware that we can change them. There's a policy for security, traffic shaping, and NIC teaming. We'll do examples of each of those in the hands-on labs. And I also want you to know that we can apply the policies for security, traffic shaping, and NIC teaming either to the switch as a whole, which would mean that the policies apply to all the port groups on that switch. And we can also go down to the port group level and apply those same policies. And if there's two policies, one at the switch level and one at the port group level, and if they're in conflict, for example, at the switch level it says yes, and at the port group level it says no, the policy that's applied at the port group level is the one that would win. Here in the vSphere web client, our first order of business, if we want to work with or look at the properties of a standard vSwitch, is to go in the interface where those vSwitches exist. And because a standard virtual switch is a logical object that belongs to an ESXi host, we're going to go to the Host and Clusters tab. Let's go ahead and go to ESXi2 as an example. And with ESXi2 selected, we could either right-click on it and from the menu select Settings, or we could go ahead and simply click on the Configure tab with ESXi2 selected. Either way, it'll take us to the Configure section for that ESXi host. And then in this pane here, we'd simply go down to Networking, click on Virtual Switches, and it would show us our existing virtual switches on that ESXi host. And then we could move this up and down if we needed more room to see additional switches. So if we wanted to modify the policies, for example, of switch 1, we'd simply click on switch 1. So we're looking at the details for switch 1 on ESXi2. And down here in the graphic, we have the VM port group called New VM Network. We have 3 virtual machines that are currently associated with that VM port group. If we expand that, we can see the names. So we've got a machine called Linux 1, VM1, and VM2. And Linux 1 is a machine that will never run because that actually is a template. But in the template, it's connected logically to the new VM network port group. And that's why it shows up here. And then as far as uplinks to the physical world, we have vmnic 5 that's being used. So if we wanted to modify the policy for this switch, with this switch highlighted, we simply click on the Edit icon, the little icon of the pencil right above the switch. So we'll click on Edit Settings. As far as the number of ports, it's set to elastic. And what the elastic simply means is that vSphere and vCenter will automatically create additional logical ports to accommodate the VMs that you have associated with the switch. So you don't need to say, I want 20 ports or 30 ports or 40 ports. It'll do it for you automatically. So regarding the 3 policy categories that we have for a standard virtual switch, we have security, traffic shaping, and teaming and failover. Let's take a look at each of those. So let's start with security. So as we discuss the security policy for this virtual switch, let's use the graphical diagram that's presented to us in the vSphere web client. So this is our vSwitch. On the left, we have VM port groups, which our VMs connect through. So let's imagine this is VM 1, 2, 3, and 4, and they're all connected via a VM port group to this switch. And then on the right-hand side, we have our VM NIC, or when we get to teaming, possibly multiple VM NICs. And we're going to use these as uplinks to reach the networks that are external to the ESXi host. So let's start off with promiscuous mode. By default, it is set to reject, which means that if VM4 is connected via this VM port group, VM4 is not going to see all the traffic from VM1, 2, and 3 that are not destined for VM4. So for example, if VM2 is going out to the internet, or VM1 is talking to VM3, VM4 is not going to see any of those frames, which is the way it should be for security purposes. However, if VM4 is an IDS or IPS, and those are acronyms for intrusion detection or intrusion prevention systems, or if we have a protocol analyzer running on this VM that's connected, and we want all the traffic to be seen on this port where VM4 is, to allow that traffic to be seen by this port that's connected logically to this virtual machine, we want to make sure that that VM and its respective port were associated with accept regarding promiscuous mode. Now, we don't want to probably do that for the entire switch because we don't want all the frames to be seen by all the virtual machines. So one of the options we have is we could apply a policy to the entire switch as we are right here, or we could go to specific VM port groups and apply policy, including promiscuous mode and accepting it, to individual port groups. And then we could tie our IPS/IDS/protocol analyzer to a VM port group that allowed analysis of all the frames. So that's the promiscuous mode option. Next, we have MAC address changes. For this example, let's imagine that VM2 has been assigned the MAC address of 22, etc. Now, a MAC address, a layer 2 address, is 48 bits in length. I'm just using 22 as an abbreviation for the MAC address that vSphere assigned to that virtual machine's virtual network interface card. If in this virtual machine, like through the guest operating system, there's a change of that MAC address. For example, let's say that it was changed to 23 something as a MAC address. The default security policy regarding MAC address changes is to accept them, which means that if some other device is sending traffic to that layer 2 address that's 23, etc., it's going to allow those frames to be forwarded to that VM. If the MAC address changes was set to reject, then if the client changed their MAC address, the switch wouldn't bother forwarding any frames to that MAC address. So from a directional perspective with this graphic here, you can kind of think of it as traffic that's trying to reach the VM. That would be referred to from the VM's perspective as inbound traffic. Thinking of it from the VM's perspective, that would be traffic inbound to the VM itself. Now, as far as the forged transmits, that's the other direction. So for example, let's say that VM2 did change its MAC address to 23 something. With the forged transmits, that allows that traffic using the source layer 2 address of 23, the one that was set by the guest operating system or the apps that are running on that computer, to be allowed to be sent into the switch outbound from the virtual machine. So one way of remembering the directions of the traffic is to first of all think of this topology with the VMs on the left and the switch on the right. And I'd like you to imagine walking in a fairly busy city in the United States and you're about to cross a street. Now in the United States, cars drive on the right-hand side of the road. So if you're about to cross the street, which way do you look first? And the answer should be you want to look left, because that's the traffic that's going to hit you immediately if you step in front of a car. So basically in the US, we look left first and then right. So if that can assist you in remembering the direction of traffic for these two options as part of a standard switch security policy, that's great. We could also refer to this as inbound and outbound permission of the frames that have customized MAC addresses. And again, that inbound and outbound would be from the perspective of the VM itself. Our next set of policies for the switch are traffic shaping policies. So when we think about traffic shaping, it's in a category called quality of service. And quality of service, if we look at the topology here, we have our switch in the middle, we have our VMs on the left, and we have our uplinks on the right. And with traffic shaping, it's regarding traffic that is outbound, leaving the VM, going into the switch, where the switch is enforcing the policy. So for example, if we had our VMs on this switch and we wanted to kind of tone them down a little bit or limit them on how much traffic they could send in, we could go ahead and enable the policy, specify the average bandwidth and the peak bandwidth, and then they would be limited by the policy for traffic shaping that we've specified, in this case for the switch, or if we wanted to apply it to a specific port group, we can set the same type of policy at the port group level, and then any VMs associated with that port group would have to abide by that policy. So if we change the status to enabled and put in the values, so by applying traffic shaping, we're controlling the outbound flow of traffic from the VMs as it goes into the virtual switch. And then our last option here is teaming and failover on the virtual switch. And in fact, for this one, what I'd like to do is I'd like to go ahead and set this up, but I'd like to do it on vSwitch 0. And currently we're looking at vSwitch 1. So I'm going to click on cancel for a moment, and we're on ESXi2 on the configure tab. We've got under networking virtual switches selected, and let's click on virtual switch 0. Because the problem at the moment with virtual switch 0 is that we have a VM kernel port labeled management network. We have one VM kernel port in it. Here's virtual switch 0 itself. But if you'll notice, for physical adapters, we only have one. We don't have any fault tolerance. If there's a physical problem or the physical switch that we're connected to using vMNIC 0 fails, we're going to lose management connectivity to this ESXi host. So I've got a separate vMNIC. It's vMNIC1. That's also already connected to our management network, but we just have not been using it so far in our course. So it's time. Let's do NIC teaming by adding vMNIC1 to the vSwitch 0. So we'll click on this icon right here to manage the physical network adapters connected to vSwitch 0. At the moment, we only have a single vMNIC 0, so we'll click on the plus symbol to add an additional adapter to this vSwitch. From our list of available network adapters, we have vMNIC1, which is sitting there waiting for us. So we'll select vMNIC1, click OK, and now it's showing up as an active adapter. Now, if we wanted to, we could click on vMNIC 0 and push it down to standby adapters, or we could further push it down with the arrow to unused adapters. But the key is we have to somehow initially associate this vMNIC with this switch. So I'm going to go ahead just for a moment and park it here in the unused adapters. Click on OK. So now it shows that both vMNICs are associated with the virtual switch. So we'll select vSwitch 0. We'll click on the little pencil to edit the settings of vSwitch 0. We'll click on teaming and failover here on the left-hand side. And here's our unused adapter. Now, truth be told, when we added the adapter, we could have just left it as an active adapter when we added it. But I also wanted to show you that here in the policy for teaming and failover, we can change it here by moving it up or down. We can also set up some additional parameters regarding the NIC teaming that are important to see. So let's go ahead and click on vMNIC here in this list of unused adapters and simply click on the up arrow, which makes it a standby adapter, and up arrow one more time, which makes it an active adapter. And then once we click on OK, we'll have two network interface cards as uplinks, vMNIC 0 and vMNIC 1, for fault tolerance for our virtual switch 0, which is supporting our management network. So regarding load balancing, sending traffic across those two vMNICs, we have a few options. The default is route based on the original virtual port. And the idea here is that the ESXi host will take some of the traffic that comes in from some of those ports and send them through one uplink, and it'll take traffic that comes in from other VMs on other ports on that switch through the other uplink. And that's the default behavior. But the other options include route based on IP hash, where it looks at the IP addresses and it creates a hash based on those IP addresses, and then based on that distributes the load across the available uplinks. Or it could do a similar calculation, but instead of the IP address, it would look at the layer 2 MAC address, and then based on that hash, make a determination on which uplink to use as it forwards the traffic. And then we have the option of using explicit failover order, which means that if we had vMNIC 0 as an active adapter and we pushed vMNIC 1 down as a standby adapter, and then if there's a failover or a problem with vMNIC 0, vMNIC 1 would kick in and be used. So we're going to leave the default of route based on original virtual port. The next question is, how do I know, says the ESXi host, how do I know when one of my uplinks, one of my vMNICs, has failed? And the default option is a link status only, meaning if the connection from the ESXi host on its vMNIC over to the physical switch, if it loses link, which implies there was a cut connection or the port on the switch was turned off, if that link goes away, it'll assume that that vMNIC can no longer be used as an uplink. Or if we have multiple vMNICs, for example, 3 or more vMNICs this would be appropriate for, it can do beacon probing. So let's say we have vMNICs 9, 10, and 11, all as uplinks. And these are connected to either the same or multiple physical switches who have interconnects between them. So it's one giant VLAN on the outside. With beacons, every interface is going to go ahead and send a beacon. So if vMNIC 11 sends a beacon, it should be seen and heard by vMNICs 9 and 10. And vice versa. If 9 sends a beacon, it should be seen by 10 and 11, and so forth. So if 9 sends a beacon and 10 sees it but 11 doesn't, and we're using beacons for failure detection, the ESXi host can say, whoa, I didn't see that beacon on vMNIC 11. That must be where the problem is. So it can assume that there's a problem with vMNIC 11 and its connectivity, and the others are fine. However, if we only have 2 uplinks, and we're using beacon probing, and vMNIC 9 sends a probe, and it's not seen on 10, who failed? Maybe there's a problem with vMNIC 9 and its connectivity, where the probe never made it to the physical network. So that's why with beacon probing, having at least 3 uplinks would be needed if we wanted to use that effectively. So in our case, we only have 2 network interface cards. I'm going to leave link status only. And then the next option is, do we want to notify switches in the event of a failure? And here's how that works. So here's our virtual switch. And let's say we have VMs 1, 2, 3, and 4. And we have 2 uplinks. And let's say we're going to 1 physical switch. And if we were doing route based on original virtual port, let's imagine that these 2 VMs are being sent through the top uplink, and these 2 bottom VMs, and based on their ports, are being sent through the bottom uplink. So from the physical switch's perspective, it's memorized the source layer 2 addresses for VM3 and VM4 here, and it's memorized the source layer 2 addresses for VM1 and VM2 here. And what the notify switches represents is that if this link fails, and the ESXi host has recognized that failure, the vSwitch knows all the source MAC addresses, and it can go ahead and take the source MAC addresses that are being used by VM3 and VM4 and pump them out in frames over its remaining uplink, which will cause this switch, the physical switch, to now learn those MAC addresses for VM3 and VM4 on this top port. It just helps convergence happen a little bit faster rather than waiting for the VMs to actually send new traffic. And then with the failback option, if we have active adapters and standby adapters, and we had a failure of one of our active adapters, and then maybe after a few minutes, the active adapter came back, failback yes says, okay, let's go ahead and send back control and start using the active adapter again, and allow the standby adapter to go back on vacation until something goes wrong again. So with those settings in place, we'll go ahead and click on OK. So now we have vSwitch 0, we have redundant uplinks with NIC teaming, and if we really want fault tolerance, we'd also repeat that for ESXi1 and ESXi3. And let's do that right now. So we'll select ESXi1, and then on the Configure tab with Virtual Switches, we'll click on vSwitch 0. And with that selected, we'll go ahead and click on this icon here regarding the adapters for that virtual switch. We'll click on plus, we'll click on vMNIC 1, and then click on OK, and then click on OK again. And then to verify the policies regarding NIC teaming, we'd select vSwitch 0. We'll click on the Edit Settings icon, the little pencil, to edit the settings of vSwitch 0, and then click on Teaming and Failover. So we have our interface already added, and now here we can specify additional policy that we want to have regarding that NIC teaming and failover. So as I look at this, we took all the defaults, so we don't have anything to touch here. So we'll click on Cancel regarding any policy changes. The network adapter is there, and let's do the same thing for ESXi3. So with ESX3 selected, and on the Configure tab under Networking Virtual Switches, we'll click on vSwitch 0. We'll click on the little picture of the wrench next to the network adapter to manage the physical network adapters for that switch. We'll click on the plus symbol. We'll select vMNIC 1, click on OK, and then click on OK. So now for vSwitch 0 on all 3 of our ESXi hosts, we now have redundant uplinks using NIC teaming with vMNIC 0 and vMNIC 1. So now on the physical world, if we had a switch port failure or one of our cables failed on vMNIC 0 or vMNIC 1, because we're using NIC teaming, we have a remaining interface that can still provide us the connectivity for vSwitch 0 and any of the port groups that are associated with that virtual switch. So have some fun in the hands-on lab as you add some fault tolerance to vSwitch 0 by adding vMNIC 1 as a second uplink that can be part of the NIC teaming solution, and I'll see you in the next nugget. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.